Good morning, everyone, and welcome to our last webinar of the year, school year, that is. And today we're going to be talking about points on the number line, but specifically operations with radicals. And this is our fifth webinar. I'm Janelle Mills. We have Lorraine Jackman, who is our secondary high school associate, and Dawn Hood, that is our middle school high school associate.
Good morning.
Good morning.
Pretty lost kids name, but I think you're now.
We want to thank you for all that you do and all that you are doing for the students here in South Carolina. We know that you're wrapping up the school year right now, so we thank you for taking time out of your busy schedule with grades and testing to participate in this webinar this morning. I'm going to start with a disclaimer of the use of artificial intelligence. The content presented is the intellectual property of the South Carolina Department of Education. By participating in this event, attendees agree they will not record, capture, or share its contents without permission. Attendees agree they will not use artificial intelligence to capture or summarize the contents of the event. The SCDE reserves the right to remove attendees using these services. We are happy to announce that we are offering 1 hour of credit recertification for webinar participation. There are 3 requirements for receiving your recertification credit. You must attend the webinar live and be an active participant. You must remain in attendance for the duration of the webinar, and you must complete the feedback form at the end of the webinar. Our purpose. Let's look at this quote. And as you do, I want you to think about how this connects to the work we're going to be doing in this webinar. Well, what we've been doing in all of our webinars so far this spring season. The focus is to demonstrate strategies to introduce our HQIM resources to teachers and encourage using these materials to provide instruction to students. So our quote for today is, algebra is but written geometry and geometry is but figured algebra, by Sophie Germain. As you look at this quote, what resonates with you? And you can take yourself off mute and respond. How does this quote resonate with you today?
Well, it resonates with me. Hi, I'm Kimberly Harrington.
Hi,
when
Kimberly.
when you think about algebra, it's a way to take literal things and write it into an algorithm. And so when I hear algebra is but written geometry, is taking what we can actually physically see and putting it in an algorithm. And geometry is what we do to figure out. I mean, the geometry is but figured algebra is because we're using, for example, if we're talking about buildings and Pythagorean theorem or whatever, the algorithm of Pythagorean theorem is the a squared plus b squared equals c squared, which is the algebra. But if you're thinking
Right.
about the distance between the top of a pole and the end of a shadow, then that is the figured algebra, which is the geometry.
Thank you. Very good. Do we have any more participants who would like to respond? Okay. Well, today we want to highlight that this webinar is really to train teachers, coaches, and support staff on ways to utilize high quality instructional materials with the 2025 SCCCR Geometry with Statistics Mathematics Standards and Indicators. Our purpose is to to equip teachers and support staff with strategies to facilitate instruction of our 2025 SCCCR Geometry with Statistics Mathematics Standards. And our purpose is to demonstrate instructional strategies that promote student engagement and conceptual understanding. So this is not a time where we're going to take a deep dive into our indicators and our indicator insights, but mostly on ways that you as an instructor, teacher can introduce these strategies and these concepts to your students, giving them a more concrete introduction and then moving into your representational and into your abstract. So during these sessions, content, of course, will be discussed because this may be the first time some teachers have taught geometry with statistics and statistics. And while some may be comfortable with the content, others may be in need of more support. So this is what this platform is. It is to support educators and teachers in helping them maybe get a better grasp of content that they may have not seen in a while or haven't seen at all and have never taught. So for some, this may be a little bit elementary, but for others, it is a place where they can get the support they need. And maybe we'll talk about something they didn't know or you don't know you need to have a question about. And this is just a way that we can introduce it, maybe give you a different way to think about the content and the concepts, and then you can move on from there. So today on our agenda, we're going to be talking about not just the points on the number line, but specifically radicals. So our standard is GSNR1, and our indicator is GSNR 1.1 that we're going to be highlighting today. So let's talk about today's standard and indicator. So when you read this standard, and I'm going to put the indicator up in a minute, I want you to think about, as you read through this, what resonates with you? What keywords tell you what students should be able to do after learning this indicator? So our standard reads, students should be representing all points on the number line as irrational and rational numbers in the real number system.
Open that.
Our indicator, that is our focus, is for us to rewrite numerical expressions of irrational and rational numbers involving radicals, including addition, subtraction, multiplication, and division to recognize geometric patterns. So our indicator, once again, is to rewrite numerical expressions of irrational and rational numbers involving radicals, including addition, subtraction, multiplication, and division to recognize geometric patterns. So our focus today is going to be on radicals. But as you read this, what keywords tell you what students should be able to do after learning this indicator? You can take yourself off mute and respond.
I didn't nobody.
When I read through this,
Okay.
I'm sorry.
Go ahead, Doc. I'm with you. Go ahead.
Go ahead.
Oh, well, thank you. I'm Tammy Adams. When I read through this, they should be able to write irrational numbers, do perform the operations with radicals, and be able to recognize patterns geometrically.
Good. And that's what we're going to talk about. Now, the standard says that they're representing all numbers on the number line as irrational and rational numbers. And this is what they need to be able to do by the end of their mathematics career in high school. The indicator is what needs to be assessed. So as you're looking through your assessments and you are creating your plans, the focus of this indicator, which is what should be assessed, is for students to rewrite numerical expressions of irrational and rational numbers involving radicals. And this would include addition, subtraction, multiplication, and division. So of course, as we talk today, we're going to be talking about these irrational and rational numbers and how they should look when we're talking about radicals. All right, now let's take a look at our indicator insight. Now, looking at this, how will it help you make sure students can master the indicator? So our indicator insight tells us that we're going to include operations with radicals, and this is the student's introduction to simplifying radicals. So as you look at this indicator insight, how does this help you make sure students can master the indicator? Student respond. And Lorraine, if it's something in the chat, let me know because I can't see the chat.
Not a problem.
Maybe I
How
missed
does our
part of maybe I missed part of the question, and I'm sorry. I do have students in here, so I may have seemed a little distracted, but can you ask that question again?
how does this insight help you make sure students can master the indicator?
And Amy Taylor has responded in the chat. Teachers will need teaching simplifying radicals. And Kelly said, I would begin with area and squares to try and help visually make connections.
Good. Yeah. So the focus, and this is an insight, and mind you, insights are just suggestions. So it kind of gives you a guiding suggestion on where you need to focus your instruction. So we already talked about the indicator insight. The indicator, which tells us that we're going to be simplifying radicals, addition, subtraction, multiplication, and division. And this insight lets you know that this is students' introduction to simplifying radicals. So for teachers that say, oh, they should have done this before they got to me, this is letting you know that no, this is their first time seeing this. So you may need to take it a little slow with them and kind of give them some grace and leeway in learning this concept.
And Dara Hyatt said, review exponent rules.
Yes, this would be a good time to do that. And we're going to talk about that coming up. So our next slide, our agenda that we're going to touch on today is, of course, our NR 1.1. And we cannot forget, of course, about our process standards. So our process standards focus for this indicator is going to be our connections, our analyze and justify, and our problem solving. All right, we're going to start with a little activity for you. So to begin, let's take a minute to think of the parts of a radical expression. Can you name the parts of this radical expression? You can respond in the chat or you can unmute to respond, naming the parts. So we
So
have our radical symbol. So our symbol is, of course, what students like to call the house.
Good morning.
Good morning.
So that I think that X there represent the base. Then we have the A being the power. And I think that one, the B represent the root. And as before, you see the radical symbol there. Yeah.
Okay, thank you. Do we have any other suggestions on our parts, our B, our
we
X, and our A? Okay.
Yeah, we do have in the chat, we have a few that responded that X is the radicand.
Okay.
And some also said X is the base, A is
Okay.
exponent, B is the index root, and X is the base.
Okay. So even hearing as we as educators are talking about our parts of our radical expression, we've had some different vocabulary words that we've used. All right, so let's look at this. And our first, the B is considered the index. So that is how it is defined, our vocabulary word that represents the index, B. Then we have A, which is our exponent. And then we have X.
This is not the time. This is not
which
the
is
time to
our
talk about this.
radicand.
Yeah. This is time for us to know it because.
So we have our X,
future
which is our
and our
radicand.
Teachers talking about that's right now. Let these people finish this and go home.
We have our X, that is our radicand, our A, which is our exponent, and our B is our index. All right, good. Looking at this problem as an introductory problem, it would be beneficial for students to begin with the concept they've already been exposed to. So looking at this, students have already learned about exponents. So covering this helps bring to light any misconceptions students may have about exponents. So as an introductory question, we're talking about Leilani and Kamari. And they wrote different numerical expressions and expanded them to show that each has a value of 16. And their work is shown below. Which student correctly wrote and solved their numerical expression? And once you know that that one's correct, how do you know? So I'm going to ask you to unmute and respond to the question. Is Leilani or Kamari's work correct? And how do you know their work is correct?
Well, Leilani's work is correct because we understand with exponents, it tells how many times you multiply the base by itself. So I see 2 4 times as being multiplied. And when I multiply 2 times 2 times 2 times 2, and I get 16. What Kamari did was multiply the base and the exponent. And basically the way Kamari's work was written, he should have multiplied 2 by itself 8 times.
Right, correct. Now, would this be a
And I
great
also have-
opportunity? Okay,
I
go
have
ahead. Sorry.
2 responses in the chat with explanations. So Marie said Leilana's work is correct because she used repeated multiplication, and Dorothy said the exponent tell how many times you multiply the bases itself.
Now, looking at this, would this be a great introduction as you're getting ready to start radicals to find out if students coming to you have any misconceptions about exponents and how you solve exponents?
And Kari said that this is a great opportunity for error analysis with kids, and Warren said Kamari is a common mistake.
Yes.
And Akili said allow the kids to proof the work. And Christy said yes, because you can easily see Kamari's misconception.
Right. And this is a way to encourage and promote collaboration in your classroom. I agree. This is a time for error analysis. You can have students compare, have these discussions, and anything that may be a little confusing for students, this would be the time for you to find that out before you get too far into the lesson. And this question is taken from Accelerate Learning, and this is in chapter 5. Now, is there another way to write a numerical expression involving exponents that will yield you a value of 16?
And just going back into the chat real fast, Tammy said yes, because I found this year students had difficulty in writing prime factorizations when we dealt with radicals, and Dara said rewriting by expanding is important.
Yes, and we're going to get into that a little further on down in the presentation. So, is there another way to write a numerical expression that will give you a value of 16? And what is an example? You can take yourself off mute or you can put it in chat.
Well, one of the ways that I help my students see the difference is multiplication in and of itself is repeated addition. So when we talk about exponents, that's different from multiplying, 2 times 8, because I would show them, I would either have them write or draw a diagram where you have 2 8 times or 8 2 times.
Okay.
Then the difference then when we talk about the exponent, which is powers, and I go over a big spiel over what power is and how much more powerful the exponents are over the regular addition, because sometimes you just got to trick them into learning.
Yes.
And then they understand that when they see that small number, and I tell them it's a small number because you're going to reuse that big number. And that's one of the ways that we go over some things, and we do different things. And a lot of times what messes them up is like 2 to the power of 2, because 2 times 2 is 4 and 2 to the power of 2 is 4. So that's where they get it mixed up, where they can multiply the exponent times the base and get that answer. So I have to show them what the difference is, and try not to use that example, because I show them that this is one of those rare cases where 2 squared or 2 to the power of 2 and 2 times 2 happens to be the same thing, but that doesn't work for 3 squared and 3 to the power, and 3 times 2. And so we show differences. and explain to them that the exponent's a little more powerful because we're repeating things. We also do that example, like, would you rather have $1 million here, or would you rather start with a penny and double your amount each day? And it shows the difference in powers and regular multiplication.
Good. That's a great example.
And
It's
we
a great
also have
example.
three responses in the chat. Eleanor said 4 times 4, or 4 to the power of 2, and Heather said 2 to the power of 2 times 2 to the power of 2, and Dara said 256 to the power of 1/2.
My name is Dorothy Dwyer.
Yes.
Since we were in the idea of writing things going in the direction of radicals,
Okay.
I actually changed the exponent 2 to the 4th to 2 to the 8 over 2. So then they could take the square root of 2 and then raise that answer to the power of 8.
Oh, okay. So we have all different kinds of ways. So what are we teaching students? There is not necessarily one way to write an expression where you will still come out with the same response. So this is a way for students to be able to think differently. They can collaborate. And this would be a great discussion in the classroom because you're not only having them explain, you're having them think through a process, and they're talking about it. So when you finish just this introduction, you should be able to see that students have a better grasp before you move into radicals. So now let's look at this slide right here. And this is considered a concrete strategy for instructional reinforcement about radicals. So what do you notice about the 2 radical examples using just the diagrams? What do you notice and what do you wonder? As we're looking at these 2 diagrams on this slide, what do you notice and what do you wonder?
There are 2 questions. There's one question in the chat: should we be teaching rational exponents with the standard? And I ensure to not use the number 2. I have students using multiple multiplication first, and the orange dots are perfect pairs.
Okay. So using our perfect pairs, and I'll get back to those questions. Using our perfect pairs, and we're just doing, this is an introduction. So this will be part of you introducing a lesson to students. We have perfect pairs, so we have 2 dots that are the same color. And then in the second part of that, we pulled out of the radical symbol those same 2 dots. And then in the third line, there's only 1 dot. Looking at the second example, we had 3 blue dots that were under the radical symbol. We pulled 3 dots from under the radical symbol, and then those 3 dots became 1 blue dot. So what do you, as a student, what would you notice about this? You can take yourself off mute or respond in the chat.
Christy said, I wonder what students would notice. Their answers would give me good information.
Yes.
This is Dorothy Dwyer again. This is very similar to how I show my students how to simplify radicals. By finding like in the first column, perfect squares, or the second column will be perfect cubes because the index was a 3.
Right.
So the way I explain to my kids is like, okay, you have, for the first column, it's a square root because the index is not there. That means automatically there's 2 there, right? An imaginary 2. So only 2 people can fit in my car. Or if they had siblings, you know how your parents will tell you, hey, you can't leave the house unless you bring your sibling with you.
Right.
Right.
Yeah.
And if they didn't have a matching sibling, then that sibling had to stay in the house. Does that make sense? They were able to leave. So I made them think that the radical was a house and you had to come out in perfect pairs. You couldn't go outside by yourself.
Okay.
In the chat, Tammy said, notice that the 2 radicals are attempting to demonstrate how to take the square root and cube root by pulling out the groups. And Eleanor asks, is each side one sequenced example?
Each side one sequence. As you move down, they're one sequenced example. Not moving across.
Okay.
Okay, so does that mean Is your symbol supposed to be over both orange dots?
Yes, but on a computer with a, it's hard to demonstrate that, but the symbol is over the entire figure.
Okay. Quite a few. So let's see. Student responses will let you know if they understand inverse operations of squaring and square root and cubes and cube root. Another person said the radical is a house party under the roof. Squares have to leave, and when they find their way outside, they come together as one. Same analogy can be used for cube roots, etc. I never thought about using the dots. I normally tell them to write the radicand in prime factorization, then find the pairs, cubes, etc.
Yes.
Someone, Janet said I really like this visual. I also use the house story. And question, are you saying the first and second problems vertically are the progression of how to simplify the radical? And Michael said dots give students a visual and tactile if you use bingo, tabs, chips, etc.
Yes. So this is just an example of if you were to give students the radical symbol and you gave them colored cubes or number blocks and asked them to demonstrate how would you simplify this number, this radical. The two that are the same color let students know that that is a pair and you are looking for pairs if your index is 2. And you want to pull out identical pairs. So whether you use number cubes and you are demonstrating using actual numbers, or just the concept of you are looking for pairs to remove from the radical symbol. And once you remove that pair, then that is the only number that you will use when you are simplifying. So that those 2 orange dots become the 1. You can take 1 away because that is a completion of that one part of the problem. Same thing with the index of 3. Yes.
So shouldn't that have the second row? Shouldn't that have an extra symbol? Like you want to show that you can represent the top and the second, like shouldn't it be the square root of the 2 orange times the square root of the blue? And then the next row would then become like it comes outside of that. I don't see how that works.
So if this was a prime number, you wouldn't pull, it wouldn't be another radical symbol over those 2 orange dots because they were all under the 1. You could show it as that, but
Well,
if
I
you're
mean,
looking
I don't see
for,
how the second and third line would be equivalent to each other. I think that's my point.
well,
Unless you
if the
put a radical or a cube root on the second row.
you don't necessarily have to do that. You can. I'm not saying you can't, because that would be a representation of a perfect square. So like if the blue dot was 3 and the 2 orange dots were 2, you could pull those 2 orange dots out, put them under a radical symbol and say, okay, you have the square root of 4. But if I've already separated it into the prime form, then all I'm doing is removing it from the radical symbol. So if you're going to keep it as, okay, you have the square root of 4 times the square root of 3, that square root of 4 would turn into a 2, and then that would become your whole number.
Right, but
And
you
so
just said square root of 4. That's my point. Is like in order for that to be stated, you have to have the square root symbol there.
If you have it as the square root of 4, if I've already separated it, it's not going to be 2 orange symbols. It would just have been 1 number, if that makes sense. It would have been the square root of 3 times the square root of 4. I would remove the square root of 4 out and multiply it times the square root of 3, and then that would give me that next line. If I've already reduced it to its simplest form, where it's under the radical symbol, it is 3 times 2 times 2, then I'm looking for the numbers that are the same. And that is what you may have students circle, and they pull that out of the radical symbol, but they don't need a separate symbol to represent that. And once they pull out that pair, then on the outside, they simply turn that into 1, 2 by itself. So I'm not saying you can't. If you have students that understand that concept, and this is for students that have never seen this before, you're trying to get them to understand about prime factorization and to take out pairs of numbers without confusing them with an extra radical symbol, this would be a way to do that.
Jeanette, I don't know. I'm trying to understand what Eleanor is saying because I would teach it that like I was split for not for the first one. Is it that you the rule says that you split the two once you find the factor like it, that the blue dot and the orange dot, do you put them on the two radicals? And then from there you can find the perfect square of the radical that is the pair. Is that what you'll do? Mr. Brown, good morning.
Good morning. If you're going to use that as a number, like what Eleanor was saying, if I was going to say that this is the square root of 3, under the radical, I have the square root of 3 and 4, and I'm pulling that 4 out just as a perfect square, but still I want to represent it under the radical symbol, then that would be an extra step. If you want students to already, under the radicand, separate the number into its prime factors, if they're already in the simplest form, I would not use an extra radical symbol for students, especially those that maybe are in your class that might need more support. You want them to be able to recognize their prime factors, and then you want them to recognize their index numbers, whether it's to the 3rd power, to the 4th power, to the 5th power, but you want them to understand that they are looking for groups of that index number.
We have
So,
2 questions.
okay, go ahead.
I think Akili was first and then Dorothy.
Okay.
Jen, your hands up.
I think I've made what I think Janelle cleared up what I'm trying to say, but I'm all right now. Thank you.
Oh,
Okay.
Thank you.
You're welcome. Dorothy? Oh.
Okay, so I see where I believe it was last name is Eleanor, I believe, or whoever. Oh, okay, I'm sorry. So the way I teach my students is that you see how we have the 2 orange dots. And I think Miss Wilson hit on it towards the end, but you see we have the 2 dots, right? Yes, we pull the 2 dots out to the front, but if the index is a 2, that means we have to make a group of 2. So every groups of 2 that are common that we take out will represent that last row. So since we only took out one group of 2s, that's why we have 1 orange dot, if that makes a little bit more sense. So like if we look at the cube root, you see we have 3 blue dots. When we took the 3 blue dots out, we only can fit 3 people in my car. So since I only have one group of 3s, that's why there's only 1 blue dot at the very end. So that'll represent that's that multiple of 3s or the multiple of 2s or the factors. I'm sorry, let me use the correct words, the factors or the prime factorization, or how many numbers that we have in that particular group. And it's always based on the index number of how many people or objects that we can group into one big group.
And
I hope that helps.
Thank you for that, because what happens is we may have index that are higher than 3 and 4 and 5, and you do not want to have, well, it is not necessarily recommended that students have that many radical symbols lined up if those are the groups that you're pulling out of the initial radical symbol, because that can get confusing. Yes, Dr. Harrington.
I guess. I understood the explanation, but it took a lot of explanation for me to, and I know how to do the roots.
Right.
I think what confused me was in the beginning with the 3 blue dots, I understood that is when we pulled it out, why it was still 3 blue dots and why it didn't go straight to 1 dot. And I guess because it's dots, I'm not seeing it. It's hard. Right. And my problem is going to be, if I can't see it, then I can't provide instruction this way. So I'm trying to see why the 3 blue dots didn't become 1 once it was pulled out, and later then it became 1. Is my question making sense? And the same thing with the
Right.
2 dots. Why didn't, for example, if it's 2 squared or 4, 2 times 2, why didn't we go on and take the square root of 4 and put the 2 out instead of putting the 2 times 2 outside and then later on making it 2? I'm not understanding that after it's taken out of the radical, how we're breaking it down even further.
Well, then once you pull that number out of that radical, then it would have been grouped. So if you want to have students circle it, and
Okay.
then it represents one number.
Right,
Once you
right,
pull
right.
that
So
number
that's
out of the
why I
group.
guess I was confused about the 3 blue dots here and then the 3 blue dots there, because it should have been that 1 dot, once it was pulled out. So, okay,
Right.
I think I got it now.
And
And
as
it's
you,
all in, I guess, how we would have
Can
to
I ask a
present it
question?
and knowing our students.
sure.
We drew it a little bit different, like with it under the radical, these two. I
Okay.
don't know if you see my picture. And then
Yes.
2 dots still under the radical, and then it coming out as 1.
Right. But the reason I'm saying that will get a little confusing right now, this is just one isolated example. But let's say we have 5 groups of pairs. Those students are going to have 5 groups of those radical symbols outside and front. So, I mean, you can do it like that. I'm not saying you can't. I'm just saying when students get to writing and demonstrating something using that concrete example, that can get a little tedious for them.
Mhm.
So if you want to just circle them, pull them out and say this becomes one number, if you want to let them know that's going to be a square root, and if you have a pair that turns into just that number, that's fine. I'm not telling you can't do it. I'm just saying in the thinking about those students that this is their first time seeing this, they're already struggling learners, having that many radical symbols can get confusing.
Yeah, I like the idea of just representing it with dots. That made it easy.
Yeah. And like I said, you can use number cubes, you can use little the tiles, that paper tiles sometimes that you have as a manipulative. And even if you don't want to use the numbers, you can actually have them break them down into prime numbers using just numbers you provide, just to give them an idea to introduce it to them. Because once they move from this, then they can move to the numbers, which would be more representational. And then you can go to the abstract where they can break down any number, not just your 4s, your 25s, your 36s, not just your perfect squares, sorry. Not just your perfect squares.
You're muted, Kathleen, if you were saying something.
I'm sorry. There's 3 of us in the room. We were just talking about it together.
Oh, okay, no problem. In the chat, Heather said they have seen roots in middle school, correct? And before that, this has caused a lot of discussion about how many dots and how many radical symbols should be listed on that second row. So I think you addressed that portion.
And like I said, that is a teacher choice. Not saying one way is better than the other, but thinking about the students and the different levels of students that you may have in the same classroom, this is just a way to introduce this concept where they can physically manipulate something themselves and show you that they have an understanding of it. And that is the whole idea of this geometry with statistics. I didn't use any numbers, but this is just a concrete way for students to demonstrate their understanding. All right, let's look at this next problem, and this is from Accelerate Learning in Chapter 5. So looking at Amir and Sophia's work, each student wrote a different equivalent expression for the square root of 18. What similarities do you see between each student's response? And what are some differences you see between each student's response? You can unmute yourself or respond in the chat. So what are some similarities you see?
The similarities I see is that they did break down 18 into factors of 18. So
Good.
Amir used 6 and 3, which are true factors of 18.
Right.
And Sophia used 2 and 9. The difference is that when Sophia broke hers down, she broke hers down using a factor of 18 that was a perfect square. Therefore, she could
yes.
further break it down. So
Right.
the equivalent expressions are correct, but it is not simplified all the way down. Amir's is not simplified. So his expression, although it is equivalent, is not what we're looking for as far as simplifying. And then we would have to, really explain that he needs to see the factors of 18 that are perfect square numbers. So then there's a discussion about what perfect square numbers are. And we do those by, diagram with actual squares, like we use the squares in the floor. They know the squares in the floor is a 1 by 1. And we talk about perfect square numbers, or we can take dots or figures, and we can all four sides would be the same amount. So then they would see that, okay, a 9 is a 3 by 3 array, and you can't do that with 6 and 3. So
Right.
that's what we would talk about. And so then at the same time, we could tell Amir where, you did a good job writing an equivalent expression, but we want it simplified using perfect squares.
Right. And he's not wrong, but
Okay.
it would not be considered its simplest form. Yes.
We have a few comments in the chat. Let's see. They both use they both use correct factors, but the equivalent expressions are not in the same form simplified. Question. So this example keeps the square root over both the factors, then simplifies perfect squares. This method counters the last example. The question does not state to simplify, but to write an equivalent expression. They both factor 18, but Sophia used a perfect square. Amir can continue to find the factor of 6. Amir stopped short of breaking it all the way down.
All right. Now, looking at this and going back to the previous slide, there was a purpose to me showing you that slide. If we're looking at this and we want students to be able to simplify these radical expressions in their simplest form, and the idea of doing this in geometry is to show a pattern, then what do we need students to look for a commonality. And when we were looking for a commonality, the reason why I suggested using the prime factors before they even get this far, if we were to have shown Amir that, okay, you can do 6 and 3, but what would be a better way to show a pattern? We want to get down to patterns, then we're going to be talking about our prime numbers. And once we get down to the prime numbers, then like in Sophia's work, instead of having that separate radical expression, a radical symbol, under her initial radical symbol, Sophia would have had 2 times 3 times 3. And with that 2 times 3 times 3, if we were looking for, of course, our index, which is 2, we would have had Sophia circle that pair of 3s. When she circles that pair of 3s, on that next line, or however you wanted to show it, you would let her know that that pair is what you pull out. Once you pull that pair out, it becomes one number, and that would be her 3 times the square root of 2, because that is what would be left on the inside. And that's why that, go ahead.
That's where with the dots, because I could see having the square root of 2 and then having the groups of 3 dots. That's why it confused me about pulling it out and it was still 3 dots. Pull it out and it automatically go down, because what I taught mine is we do the prime numbers. When you see 2 times 3 times 3, because it's a square root, or the root or the index root is 2, then because I see 2 3s, I can pull it out and it becomes 1 on the outside. And
Right.
so I like that, because now you can take the picture and put it toward the numbers and they see how it matches.
Right. And that's why I showed you like that, because if it was a student, they're most likely going to show you like that. And that's just an extra step for them. But if it's a kid that understands, and once I circle it and pull it out, it becomes 1, then that's fine. I don't want to dictate. I don't want to dictate that part. But as a way to show them using concrete examples, that was just an example of how they can use it using dots, like I said, colored those little cubes. However, but before they get to using numbers and understanding that the same color is the same number and we want it in our prime factors, that was just an example and a reason to show why it would be a little easier as you progress into these radicals and get ready to do addition, subtraction, multiplication, and division, how introducing it and giving them an understanding of that at first would be a lot. It would probably help you a lot before you get further down the road.
Okay, there are a few more comments in the chat. It provides a moment to share that we break radicals down until the only remaining factors are 2 and prime numbers. There are tangential conversation opportunities here getting into patterns and such. Another comment, students need to look for perfect squares or cubes. And another comment, this is where students knowing square numbers will be beneficial. At least the squares of 1 through 25. Student misconception in Sophia work. Students would put the 3 behind the square root of 2. That's a misconception. And split the number into the product of a greatest perfect square and some other number.
Okay.
And so before we go to radical form, it's best to teach prime factorization first. Guess that's a comment / question.
Well, this would be, they should already know prime numbers coming into this class, this course. If you want to reinforce what they've already learned, this would be a way to do it. By no means should you stop a lesson and formally teach prime numbers at this stage of learning. Giving them examples, having them figure it out is probably a better route to take. And I will reiterate this. There are only about 33 indicators. 33 indicators that we're teaching. Some of these classes are a full year, 180 days. There's time to have students explore these concepts. There is not a rush. You know, we do not dictate any pacing guides. That is a local decision. But unlike in the past, it's not like, oh, I got to get this done. I got to get this done. I got to get this done. I only have a week or 2 days to get this indicator or this standard mastered with these students. You have time.
And speaking of time, we have about 12 minutes left. So here's some more comments. And here's a question that wasn't answered before. They
Okay.
have seen roots in middle school, correct? And let us not worry about prime factors, but perfect squares. That was one comment.
Okay. Now, I will remind you that this would be a great time to review vocabulary words. So words such as factor, integer, prime factors, radicand, and index. These are all words that students should be using repeatedly so they understand and they're able to recognize it and to give those as examples as they're talking.
Hey, son,
So-
how are you?
As students create their
Good.
own rectangular
I'm
figure,
11 minutes out. I'm
ask
being finished with
them,
this webinar. So I got my mouth
Just remember
covered
to
so
mute
I could talk.
yourself
So you want me to call you
if-
back? Are you already at work?
Just remember to mute yourself if you are not answering a question. Thanks.
all right, how could this be modeled concretely before moving to an algorithm to solve? What patterns could a student look for? You can place your response in the chat or you can unmute and respond. So we're asking students to find the perimeter of this rectangular figure. What patterns should they look for when they want to simplify these radicands?
Let's see, in the
Well-
chat, we have, let's see. My 10th graders did have some issues with knowing prime factorization. I had to end up showing them how to use the NSPIRE to give the prime factorization. And answer to your question right now is multiply 45 and 20.
Well, what I was gonna say is, because we're finding the perimeter and, you know, they know, and they need to stress with finding the perimeter, so they're adding the 4 sides. Now they're looking at, oh, I got to add square root of 45 and square root of 20. How do I combine those? So that's why I would have them, if we could work on breaking this down into the square root of 45 being 9 times 5, and they get 3 square roots of 5, and then 2 square roots of 5 for 20, then it will be easier, because I tell them, if they see a common square root, like the square root of 5, then that's like combining like terms. Those terms are alike. So now they're adding 3 and 3, 2 and 2, and then they leave the square root of 5. And so because it's perimeter, they can break it down, because they deal better with smaller numbers. They see that square root of 45 and in the square root of 20, it's like, oh my God, it's a big number. But if they go ahead and get in the habit of breaking it down, then they'll see they have a common radical at the end, and they can combine all 4 numbers and get 6 to 10 square roots of 5 as the perimeter.
Yeah, and a way that you could model this with students, if you gave them this problem and you said, okay, how can I represent the square root of 5 using these 3 colors? And you have 2 of the same color and 1 is different. That's going to make them think, oh, what number could be the same and what number is going to be different? But as I look at my sides, what number do they have in common that remains under the radical symbol? Then they would understand the pattern is that square root of 5. It's going to be the square root of 5 all the way around. That's going to be what stays under the radical symbol. And if that's a way that you can concretely have them show you that they understand it before moving to a number and say, okay, it's the square root of 9 times 5 under 45 and the square root of 5 times 4 underneath the other side to get 20. All right, let's look at this question right here. We have, which of the following expressions do you think can be combined? You can place your answer in a chat or you can respond. And how do you know your responses can be combined? And there is something we can discuss once you figure this out. So which of the following radical expressions do you think can be combined? Unmute and respond.
Before you get your responses, there were a couple comments from before, but one of them I think you would like to hear. This is a wonderful presentation.
Thank you. So which of the following of these can be combined? And how do you know?
So far, the answers are CFD.
Okay. We do have a C, we do have D, we do have F.
And the explanations, it can be combined with the same radicands.
Ah, because they have common radicands. Okay. We also have G, but G is a little different, and there's a reason. What's different about G and F?
Simplify G first, then we combine.
Right. You can simplify it. Square root of 49 is a perfect square. The square root of 4 is a perfect square. And so they can be reduced and then combined. Not combined right off, but reduced and combined. This is an example taken from Accelerate Learning Chapter 5. I will caution you, when you find this example in Chapter 5, the answer choices will be your C, your D, and G, but F is not highlighted. So if your students were to give you this and you're just looking at the key by itself, the key is only going to give you C, D, and G. And I added the letters in to make it a little easier to respond, but that is something you might want to make a note of.
Okay, that was a good problem. Also, you have a 5-minute warning.
Oh, thank you. All right, so looking at this example, this is another example of using a trapezoid to find a model, and what pattern would students be able to look for when performing operations with radicals? And this is taken from Savas Envision. And again, the pattern we want to look for is we would want students to understand that they could reduce the radicand to make sure that it has the same, a perfect square, but the same number under the radical symbol. Because they would be adding something in the square root of 6. And this problem would be 4 times, so it'd be 2 times the square root of 6. So when they add the bases, it'd be 2 times square root of 6 plus the square root of 6, and then it'd be 1/2 the height. So that's just a way for students to be able to recognize a pattern when they're talking about geometric figures.
There was a question about what book are you referring to? This was from Accelerate. Oh, right. Yes. It's
Right, so-
Accelerated Learning. Mhm.
This particular example is from Savas
Savas.
Envision. Yes, and it is chapter 3.
Mhm.
So I'm introducing, remember at the beginning we were talking about using our HQIM. I'm giving examples from different curriculum just so you'll be able to recognize it, and then you may be able to use what you need to use for your instructional purposes, just examples that you might want to use in your class. All right, here's another example from Savas, and they give you more of an algebraic look at it, and there's nothing wrong with that, but just for concept, concrete purposes and showing your students, that's why I started with that, but then they would move into this as a more abstract and a representational design. So this is how they just move the curriculum. So if you're doing your CRA model, you might want to start with some pictures, have them demonstrate how they know what number goes under the radicand before moving into a more abstract concept with go from the pictures to the numbers to using actual algorithms. All right, here's some examples of dividing radicals using your equivalent expressions. And these are just ways for you to demonstrate with your students. Not all of these will be used, and there's not always a concrete way to do some of this math. Sometimes you just have to do your representational and your abstract, and that's fine. But if it is a way for students to be able to demonstrate their understanding using something that's concrete, something they can manipulate, then we encourage that because it will help support and reinforce their learning. Any questions?
Yes,
From
the
today.
question from before was, are there roots in middle school? And yes, it is in 8th grade where students are analyzing patterns of perfect squares and perfect cubes to evaluate square roots and cube roots.
Any other questions? All right. I thank you for
I'm
attending
sorry, I do
today's
have one question.
session. Okay, well, I'm gonna go
Yes.
ahead. Let me get
Um,
to the feedback survey, and you can, as before, you can log on to our PLO feedback survey